and our goal is to compress X, which we know comes from some alphabet script X, and X is distributed according to Px. So both the encoder and the decoder, or the compressor and the decompressor, have access to Px, and the goal is to and our goal is to construct a prefix-free code which minimizes the expected length. And we've seen that any prefix-free code must necessarily satisfy what is called Kraft's inequality, which says that summation over all x 2 to the minus k of x is less than or equal to 1. And this is not just a necessary condition, it is in some sense also sufficient. By that I mean that if we have a set of lengths k1, k2 up to km which satisfy Kraft's inequality, then we can construct a prefix-free code with the corresponding lengths. Right? And in the last class, we also saw that given any prefix-free code, any variable length prefix-free code, the expected length of this code must always be greater than or equal to the entropy. And equality happens only if the code is only if the PMF is dyadic. Right? So you have equality if and only if P of x or K of x is equal to log 1 over P of x. Right? So only if log 1 over P of x is an integer and the corresponding length is equal to log 1 over P of x, you have an equality in this particular case. So now that we've seen that the expected length is always lower bounded by the entropy, let us try to construct codes which get as close to the entropy as possible. In some cases, it may be possible to achieve entropy, but in some cases, it may not be possible. So in that case, what is the best expected length that we can achieve? So we'll see three code constructions in this class and the next. The first, something that I already introduced in the previous class, was called the Shannon code. We'll also see two other codes. One is called the Huffman code and the other is the Shannon-Fano-Elias code. So the Shannon code does the following. We'll make use of Kraft's inequality to construct the Shannon code. So we choose k of x. Instead of designing the code in the very beginning, instead of constructing the code words, we'll start by constructing the code word lengths. So we'll fix the code word lengths and then we'll design a tree code with the corresponding lengths. So we choose k of x to be the ceiling of log 1 over p of x. So p of x is known to us. So this choice of k of x is well defined. So the corresponding code word lengths are going to be the ceil of log of 1 over the probability. Now, if these code word lengths satisfy Kraft's inequality, then we know how to construct a prefix-free code with these lengths. So all we have to do is verify that this choice of code word length satisfies Kraft's inequality. And to see that, notice that k of x is always lower bounded by log 1 over p of x. So k of x is ceil of log 1 over p of x. So this is always less than or equal to log 1 over p of x, and it is greater than or equal to log 1 over p of x, and less than or equal to log 1 over p of x plus 1. Right? So if we use the first inequality, we get that 2 to the minus k of x is less than or equal to 2 to the minus log 1 over p of x, which is the same as saying that 2 to the minus k of x is less than or equal to p of x. So now if we see what happens to the Kraft sum, so summation over all x in x, 2 to the minus k of x, this is simply summation over all, this is less than or equal to sum over all x of p of x, which turns out to be 1. So this choice of k of x satisfies Kraft's inequality. And now that we know that this satisfies Croc's inequality, we can construct a tree code with the corresponding code word lengths. Now, for a general P of X, what is the expected length that we can achieve? Or can we at least get a bound on the expected length? How close is this to entropy? Let's substitute for K of X. So K of X is log CL of log of 1 over P of X. And we know from the second inequality over here that this is less than or equal to sum over all x in X of P of X log 1 over P of X plus 1. Right? And what is this equal to? This is the entropy plus 1 bits. So the Shannon code achieves an expected length which is between h of x and h of x plus 1. So this has to be satisfied by any prefix-free code, but we also know that the Shannon code achieves an expected length less than or equal to h of x plus 1 bits. All right. So let's see an example of the Shannon code. Okay. So let's say that I have 5 symbols in my alphabet: A, B, C, D, and E. And they have probabilities, let's say 1/4, 1/8, 1/16, 1/16, and half. Okay. So in this case, what is log 1 over P of X? So CL of log 1 over P of X. Yeah, so it's 2, 3, 4, 4, and 1. Right, so this is log 1 over P of X. Okay. So now we want to construct a code with these code word lengths, right? So how do I do this? I'll take the complete binary tree of depth equal to L max. What is the maximum length in this case? It is 4. Right? So let's look at the tree of depth 4. Okay, so this is a complete tree of depth 4. Let's label the edges of the tree with zeros and ones. Okay. All right. So now I want to construct a code with these lengths. So let's first look at the code word length. Look at the code word for A. So A has length 2. So I keep going to the left. I go here and then go here and stop at depth 2. So this can be my code word for A. So A has code word 0, 0. Let's see what happens to B. So B requires a code word of length 3. So I keep going to the left. I go one step to the left. I can't go to the left once again because this is the code word corresponding to A and it has to be a prefix free code. So I go one step to the right and then I go one step to the left. So I have a code word of length 3. This will be my code word for B. So B has code word 010. Okay, so now let's look at the code word for C. Once again, I go one step to the left, one step to the right. Now I can't go to the left because that is already occupied by B. I go to the right and then to the left. So this will be my code word for C. So the code word for C is 0110. Okay, let's look at this for D. So go to the left, go to the right, go to the right, and go to the right again. So this gives me the code word for D. So it is 0111. And E has a code word of length 1. So I can go one step to the right and choose this as my code word. The code word will be just 1. Okay. So this is how you would construct the Shannon-Fano code. Sorry, the Shannon code for a particular probability mass function. Any questions so far? Yes, any questions? Okay, so what is the expected length of this particular code? Fifteen by 8 bits. And what is the entropy? So this is also equal to 15 by 8 bits. Right? So this is one example of a source where the expected length is equal to the entropy. And can one of you tell me why we got the two to be the same? Yeah, so the probability mass function is dyadic, and therefore the expected length is equal to the entropy. Right? And you can see that as long as we have a dyadic distribution, for any dyadic distribution, the Shannon code achieves a rate equal to, or an expected length equal to the entropy. Okay, so this is great. We've got something that gets very close to entropy, but in case the probability mass function is not dyadic, then this is not a good code. So let's take an extreme situation where I have three symbols, A, B, and C. And let's say the probability of A is, say, 0.5. The probability of B occurring is 0.499, and the probability of C occurring is 0.001. Okay. Now, just by looking at these probabilities, okay. So in this case, can you tell me what is the what are the corresponding code word lengths for this choice of P of A, P of B, and P of C? So if I wanted to design a Shannon code, then what would be the lengths? Right, so A would get a length of 1, B would get a length of 2, and C would get a length of 10. Right? So log 1 over C of log 1 over P of X turns out to be these. Now, can one of you say, is this a good code, or do you think this is a bad choice of code word lengths? Can we do something better than this?
We can do better.
Okay, and why? How can you do better?
Uh, we can just have 1, 2, and 2.
Exactly. So you can choose uh, the code word lengths 1, 2, and 2 would still give you a prefix-free code, but would have a smaller expected length than what you would get using these lengths. Right? So the Shannon code does badly if there are symbols with very small probabilities, or if uh, if it's very far from being dyadic in some sense. Right? So, but still, nevertheless, you'll still get an expected length which is at most h of x plus 1. Right? You can do the calculation in this case, and you'll still get something close to h of which is less than or equal to h of x plus 1. So clearly, the Shannon code is not optimal. Let's see if we can design a better code. So the second code that we'll see is called the Huffman code. And the basic idea behind the Huffman code is the following. So let us say that we have just three symbols. Okay. Uh, so we have three symbols A, B, and C with probabilities P of A, P of B, and P of C. Okay, so P of A is greater than or equal to P of B, which is greater than or equal to P of C. Now, irrespective of what the numbers are, P of A for P of A, P of B, and P of C, can you think about what would be an optimal code for this in the sense of minimizing expected length? It would be 1, 2, 2, right? So 1, 2, and 2. Any other choice would give you a larger expected length, right? And another basic idea is that if you have two symbols with the least probability, then if you have two symbols of roughly the same probability, then these two should get the same code word length. All right. So so the Huffman code is basically the Huffman coding algorithm. It is going to be an iterative algorithm. So once again, so unlike the Shannon code where we first constructed the code word lengths and then designed the code, in the Huffman code we're going to design the code words themselves one after the other. And so we know what is the optimal code for three symbols, and we know what is the optimal code for two symbols, right? So P of A greater than or equal to P of B, the best code would be 0 and 1, right? And corresponding to code word lengths 1 and 1. So code word lengths 1 and 1, or code words 0 and 1, right? So we know what is the optimal code for two symbols, we know what is the optimal code for three symbols. So basically what we do is try to reduce our alphabet to a smaller and smaller alphabet till we get down to one of these two cases. Okay. So let's look at this for let's look at this as an example. All right. Uh, Let us say that we now have four symbols, okay, with some probabilities: P of A, P of B, P of C, and P of D. Okay, and let us assume that the probability of A is greater than or equal to the probability of B, which is greater than or equal to probability of C, greater than or equal to probability of D. Okay. Uh, the way the Huffman coding algorithm works is, it tries to iteratively reduce the size of the alphabet. So now we have an alphabet of size 4. There are four symbols. I'll merge two symbols of the alphabet to get a super symbol. So if I merge these two, then the probability of the merged symbol is P of C plus P of D, right? And okay, so this is P of C plus P of D. Now we have three symbols. Let me call this merged symbol as CD. Okay, so now I have three symbols, A, B, and CD, with probabilities P of A, P of B, and P of CD. Okay, so let's call this C or D. Okay, so now once we have this, we are down to three symbols, and we know how to construct a good code, right? So if it is the case that probability of C plus probability of D is still less than or equal to probability of B, then the optimal code words would be 0, 1, 0, and 1, 1. Okay, this is one choice, right? So for this super symbol CD, we get a code word 1, 1. And for C and D separately, I can just put 0 and 1, right? So A would get a code word of 0, B would get code word 1, 0, C would be assigned a code word 1, 1, 0, and D would be assigned a code word 1, 1, 1. Let's see a more concrete example. Okay, let's perhaps look at the example that we had earlier. So it is 1/4, 1/8, 1/16, 1/16, and half. So 1/4, 1/8, 1/16, 1/16, and half. A, B, C, D, and E. So the first step in the Huffman algorithm is to combine two symbols with the least probabilities. And in this case, it is C and D. So C and D have the least probabilities here. I'll merge these to get C dot D. And this has probability 1/8. Right? Now I'll combine this with, so now I have an alphabet of size 4, A, B, C, D, and E. And what are the symbols with the two least probabilities? They are B and CD. So I'll combine these, I'll merge these two together to get a super symbol B, C, D. Okay. And what is the probability of B or C or D occurring? It is 1/8 plus 1/16 plus 1/16, which is 1/4. Right. So now I have three symbols: A, B, C, D, and E. The two symbols with the least probabilities are A and B, C, D. So I merge these two to get A, C, or D. And now I combine these two, and the probability is equal to 1. Right? So if I view this in the form of a tree, starting with this as the root, then I have the following tree. On one hand, I have E. On the other hand, I have A, B, C, or D. I look at two more folks. On one side, I have A. On the other hand, I have B, C, D. On one side, I have B. On the other hand, I have C, D. I have C, and I have D. So now that I have this tree, I just label the edges of the tree with zeros and ones. And I automatically get a prefix-free code. So the code word for A will be 2, will be 0, 0. The code word for B will be 0, 1, 0. The code word for C will be 0, 1, 1, 0. The code word for D will be 0, 1, 1, 1. And the code word for E will be just 1. All right. Any questions here?
Hello, sir. In,
Yes.
in this question, it is not in the decreasing order, sir.
What is not in the decreasing order?
Means 1 by 4, 1 by 8, 1 by 16, like this,
Sure,
sir.
sure. Okay, I've not reordered it, but at every step, I'm always merging the two symbols with the least probability.
Yes, sir. This is the case.
Right? That's it. So that is it. Uh, of course, I mean, to make it visually easier, maybe it would be useful to just order them in the order of decreasing probability. But the way the Huffman coding algorithm works is that at each step you merge two symbols with the least probability and get a super symbol, and then you keep repeating this till you have no more symbols left to merge. Okay. So the other thing to note is that both in case of the Shannon algorithm and in case of the Huffman algorithm, the code words are not necessarily unique, because the code word assignment is not necessarily unique, because I can always interchange 0 and 1 in this particular uh, labeling, right? So I can always assign this to be 0 and this to be 1, or I can assign this to be 0 and this to be 1, and I basically effectively get the same thing, right? It's still a prefix free code, uh, It's a different prefix-free code, but the code word lengths are the same.
Sir,
Yes, Ashok.
you have mentioned at each stage we merge symbols with least probability. What happens if we have four 1/16s and one by 4 and one 1/2?
So
Do we?
again, it doesn't matter. You merge any two symbols with the least probability. So if I have three symbols, so for example, yeah, you have 1/16, 1/16, 1/16, 1/16. You can effectively merge two symbols, any two symbols, with the same probability. So you could merge these two or these two. It doesn't matter, at least in terms of the expected.
Yeah, and after that, sir, like we will get the super symbol will be 1/32. After that, do we merge super symbol or do we merge these two?
So let's see. Go back. Okay, so I have 1/16, 1/16, 1/16, 1/16, and the other. What are the other probabilities you want to take?
1/4 and 1/2.
1/4 and 1/2. Right. So I'll first merge maybe these two symbols. I'll get a super symbol with probability 1/8. Now, what is this? What are the two symbols with the least probability? They are this and this. Right. So I'll merge these two to get a super symbol with probability 1/8. Right. Now, which are the two symbols with the least probability? They are these two super symbols. So I'll merge these two to get a super symbol of probability 1/4. And then I'll merge these two to get super symbol of probability half. And then these two to get a symbol of probability 1. Right? And then I can assign code words, label these 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So the code words are going to be 1, 0, 1. I always go this way. 0, 0, 1, 1. And then 0, 0, 1, 0. 0, 0, 0, 1 and 0, 0, 0, 0. Right?
Excuse me, sir. Here
Yes,
the
sir.
pairing was like very obvious in the sense that these were the only options that could have been paired. But if we had a single bit with a probability, like a single alphabet with a probability of 1/8, and after combining these two, we had a probability of 1/8 and 1/8, 1/8 each. So how would we pair in that case?
So maybe so at every stage you just follow the same rule. So take any two symbols with the least probability, merge them to form a super symbol. Doesn't matter which two you combine.
Okay.
Does that answer the question, or was it something different?
I meant, sir, that here after combining two bits, we get a probability of 1/8 for
Correct.
two cases. So, and let's say that we had an individual probability of 1/8.
Okay.
So after that, we'll have three probabilities of 1/8. Two of them referring to two bits combined, and one of them referring to one alphabet only. So my question was, which one should we combine, or there's no particular
So
way
these
in
two are going to give you two different Huffman codes, but essentially you'll get the same expected length.
Okay, sir. Thank you.
Sir, what if 1/4 wasn't there in the same question, sir?
So what do you mean? If 1/4 was not there, what else would like instead of that? What?
If 1/2 was only there, rather than 1/4.
So then it would not be a valid probability
Okay.
mass function,
Yes,
right?
sir. Yes, sir. Sure. Yes, sir. Sure.
So they have to sum to 1. Yeah. So if you had like say 3/4 instead of 1/4 and half, then you would just terminate at this step where you would get 1. This way 3/4. Anyway.
Okay.
right? Any other questions?
So just a quick question. We can play around with zeros and ones at any level, right?
Yes,
Suppose
yes.
the first one is top one is zero, bottom is one, but the second is maybe one and zero. That's fine.
Sure, yeah. So all of these are going to give you the same expected length. And all of them are going to be prefix free anyway. I can just interchange any two of these. I can just make this a 1 and this a 0, and it doesn't matter. But then there might be, I mean, depending on how you would implement it, storing the code. So note that whenever you're compressing a file, you have to store two things. One, the code word itself, but you also need to store the code, right? Or you need to store the probability mass function, and the decoder has to reconstruct the code. So as long as you do it in some systematic fashion, which is known, which is pre-agreed upon by the encoder and the decoder, it's fine.
Sir, can you please repeat what you just said? Like,
So yeah, as I mentioned, so this tree, once you get this tree, the way you label the edges doesn't matter. So as long as at each level you have a 0 and a 1, it's okay. I can interchange this with a 1 and this with a 0. But whatever rule you use, it generally has to be systematic for the sake of implementation, because after all, both the encoder and the decoder has to construct this tree, right? So the
yeah,
encoder stores the so ultimately the decoder gets to know only the probability mass function, which is perhaps stored as a header, and the decoder has to first construct this tree, and typically whatever is the simplest way to assign like labels to the tree, it's good enough. But effectively it doesn't matter.
fine.
Yeah, and also for a given set of probabilities, so depending on which two symbols you decide to merge, you could have different codes. So for example, let's go back to one of the cases that one of you pointed out. Let's see, maybe something simpler. Yeah, 1 by 16, 1 by 16, 1 by 16, 1 by 16, and let us say that I had a 1 by 8, and what else do I have? 8, and say 1 8, maybe not 1 8. Okay, 1 8 and half. Okay, so I combine these two to get a super symbol with probability 1/8. Combine these two to get a super symbol of probability 1/8. Now I have to make a decision. I can either combine these two to get a super symbol of probability 1/4, or I can combine these two to get a super symbol of probability 1/4, or I can combine these two to get a super symbol of probability 1/4. Right? So in each case I get a different code. So I can combine these two to get a super symbol of probability 1/4. Next, I combine these two to get a super symbol of probability 1/4, and then half, and then 1. Right? So this gives me one code, and the code word lengths are going to be something. But then I could also have combined these two symbols in the third step to get a super symbol of probability 1/4, and then proceeded. And the corresponding code word lengths would have been different. Right? So both the code word lengths and the code words themselves could be different, but irrespective of what you do, you will still get a code with the same expected length. So all these codes are going to be optimal. All right. Any questions? Yes, so Adhyasa, there is a way to prove it, and we'll see that maybe in the next class or so. We'll see, in fact, we'll see that the Huffman code, irrespective of how you do this merging, the Huffman code always yields a code to give, so it always gives a code with the minimum expected length. Right? So every Huffman code for a given set of probability mass functions gives you the same expected length, and in fact it is the minimum possible expected length that can be achieved by any prefix-free code. So at the decoder, how does so given a set of probability mass functions, or given a probability mass function, the encoder and the decoder should merge the same set of symbols in a particular sequence, and that is indeed so. So the way the encoder and the decoder construct the tree has to be the same, and for that you can impose a certain rule. Maybe if this is a, if you have A, B, C, D, E, F, G, right, and then you merge symbols together to get whatever these two gives you A, B, the C, D, right? So one rule that you could do when constructing the tree is that you always, if there is a tie, if there are 3 or more symbols with the same probability, then you can decide on some rule. As long as you fix it, it's fine. So maybe the decoder and the encoder could agree that if there are 3 or more symbols or super symbols with the same probabilities, then you always merge those which are the least in the sense of maybe lexicographical ordering. So in this case, we can merge A, B, and C, D, or C, D, and E, or A, B, and F, whatever. So you can always decide to merge symbols which are alphabetically the first. So lexicographically they are the least. So I will always decide to merge A, B, and C, D if there is a tie, or if there is something like AC and B and EF, then I will always decide to merge lexicographically the least, which could be AC and B. So this is one way to do it. Right? And when you merge, you will always get a 1, since it's irrespective of whether the probability mass function is dyadic or not, you will always get a 1, because at each symbol you're just summing up the probabilities, right? So at each step, so the total value at the root is going to be the sum of the probabilities of the super symbols below, which is essentially equal to the sum of the probabilities of all the symbols, which will be equal to 1. Right? Any other questions? Okay, so maybe this is a good time to have a quiz. The link to the quiz is in the chat box. You can take maybe 1 more minute. Is there anyone who has not submitted the quiz yet? Anyone yet to submit? Okay, so if not, I'll stop accepting responses. Okay, so we've seen two of the codes that I promised to show you, the Shannon code and the Huffman code. Now, before we analyze the performance of the Huffman code and compare this with the Shannon code, let us see the third code, and then we'll analyze the performance of all of these codes together. So the third is what is called the Shannon-Fano alias code. Right? And the Shannon-Fano alias code is constructed in a slightly different way. So unlike the first two codes that we've seen, where it has a nice interpretation in terms of constructing the tree, the Shannon-Fano alias code works in a very different way, and it basically does so by looking at the values of the probabilities and then playing around with them. So suppose that we have, say, a certain number of symbols, x1, x2, up to size of x. So let's say that the alphabet is, say, x1, x2, x3, up to, let us say, xm. Okay, so there are m symbols in this particular alphabet, and the corresponding probabilities of these symbols are, let's say, p of x1, p of x2, up to p of xm. Okay. Now we've seen that the CDF of this particular distribution, the cumulative distribution function, f of xi. So this can be written as summation I j going from 1 through I of p of xj. Right? And so I'll define something which is similar to the cumulative distribution function, which I call the modified CDF. So I'll call it f bar. So f bar of xi will be summation j going from 1 through I minus 1 of P of xj plus P of xi divided by 2. Okay. So it looks similar to the CDF, but in fact it is not the CDF. Okay, so this is what I call the modified CDF. All right, so if I draw a picture, so let's take an example. Let's say that I have, say, 4 symbols, x1, x2, x3, and x4, and the probabilities are 0.3, 0.2, 0.4, and 0.1, right? So the corresponding, so what is f bar of xi? Yes? It's 0.15, 0.4, 0.7, and 0.95. Right? So if I draw this, so I have x1, x2, x3, and x4, x2, x3, and x4. Then at x1, the probability of x1 is 0.3. The CDF would be 0.3. That for x2 would be 0.5, 0.5. For x3 would be 0.9, and x4 would be 1. Right? So the modified CDF is basically the midpoint of these values. So this is f bar of 1, this is f bar of 2, this is f bar of 3, and this would be f bar of x4. Right? This would be f of x, and this would be f bar of x. So this is f of x1, f x2, f of x3, and f of x4. Right? So anyway, so we'll continue the discussion in the class tomorrow. If there are any questions, then feel free to ask them now.
Sir, we saw
Yes.
that why we needed Huffman code because Shannon code is performing badly when the PMF is not dyadic.
Correct.
Why do we need this third code? Is there some case where Huffman code is failing?
So we'll see that although the Huffman code is indeed optimal, so we cannot beat the Huffman code in terms of the minimum expected length, but the Shannon-Fano-Elias code, as we'll see, is going to be a natural step in constructing a code for larger sequences. So the problem with the Huffman code, as we'll see, is that, okay, so if you have a sequence of length 1, you can construct the Huffman code and it will be optimal. Now let us say that I have a sequence of length n, xn, right? If I want to construct a Huffman code for the n length sequence, not symbol-wise, if I want to do, say, block-wise encoding, then constructing the Huffman code and then storing it, this is extremely complicated and is difficult to do. In order to reduce the computational complexity, we'll use an extension of the Shannon-Fano-Elias code, which we'll call the arithmetic code.
And sir, I guess you'll discuss in the next class, but what's the order how do we decide x1, x2, x3, x2? Which comes first?
It doesn't matter. So ultimately, as long as both the encoder and the decoder decide to order the symbols in the same order, it's fine. Right? Any other questions? Okay, if not, then we'll end the meeting for today. Yes, Anurag, you wanted to ask something?
So this is outside the class section. I waited so that the class was being answered. So, sir,
Yeah.
I attended this talk about HEVC and X265 compressor encoder.
Sorry, could you please repeat? Your voice was very low.
I attended this talk about HEVC, the video compression
Okay.
standard.
Okay.
There, the speaker mentioned that encoders and decoders are not constructed by the same people. Like, we don't actually need to have any pre-agreed set of rules, so that like whatever we see here, we see that encoder and the compressed form depends on the encoder, so decoder needs to know something about the encoder, right?
Sure.
But how can that be achieved? Wherein I can do any sort of interesting things on encoder, but decoder will always be able to decode it because it's not made by the same people.
So the decoder will have to know something, right? Because otherwise you cannot reconstruct. So the decoder has to know what rules the encoder is using.
Okay. Like
So
it's
so yeah, go ahead.
so it still needs to know some basic information.
Sure, of course. Because otherwise the compressed file is just a sequence of random bits, right? There's no way you can construct the original file from this file.
And